Normally, our sample size is appreciably large, whereby we don't have to worry about, if our parent population is plagued with outliers. But if it is, our sample size should definitely be much larger than size 30. Again, the central limit theorem says that if your sample size exceeds size 30, then the sampling distribution of your sample means will always be approximately normally distributed, regardless of whether the parent population is or is not normally distributed. Central limit theorem says if your parent population from whence your samples are chosen is normally distributed, then your sampling distribution of your sample means will always be normally distributed regardless of the sample size. Even for small sample sizes, that would be true. All right, here is the test statistic that we're going to, the formula we're going to use for our test statistic. It is right here. Notice we're going to reach into our parent population and pull out a sample of size lowercase n. We're going to compute its mean. Then we're going to take the mean of the sample and subtract off the purported mean of the population under the null hypothesis assumption. For that reason, ladies and gentlemen, oftentimes in most textbooks, they have a little subscript of 0 here. This is, okay, the mean of the unknown mean of the population under the null hypothesis. And that little 0 there reminds us that it's what the mean is being set equal to in our null hypothesis statement. Okay. This is going to be divided by the standard error of the sampling distribution, which is to say the standard deviation of the population divided by the square root of the sample size. So this is our test statistic value here. Okay. And this is usually the second, well, actually, it's the third step of our 5-step procedure in conducting hypothesis test. Okay. All right, so these are the 5 steps in conducting a z-test, assuming our population standard deviation is known. Step number 1 is you, first of all, clearly have to state the hypotheses that are going to be tested. And you need to identify which hypothesis is the claim that we are testing. Sometimes the claim is our alternative hypothesis statement, but sometimes it is the null hypothesis statement. It just depends, okay, what the claim is. And of course, last week we've seen that hypothesis tests require that we have a null hypothesis statement, and we also have an alternative hypothesis statement, okay? And notice with the alternative hypothesis statement, we learned last week that you're always going to have one of 3 symbols, either strictly greater than or strictly less than or not equal to. It's got to be one of those. Step number 2 is setting the level of alpha, your level of significance. So basically, you need to determine at what level you're going to test these hypotheses. Normal levels that we test hypotheses would be the 1% level, 0.01, or the 5% level, 0.05, or we test many times at the 10% level of significance. Of course, the level of significance alpha is a probability, and it basically indicates the probability of committing a type 1 error. A type 1 error is rejecting a null hypothesis when the null hypothesis is indeed true. That's one of the worst things that you could commit when conducting hypothesis testing, is to commit a type 1 error. And again, that occurs when you reject the null hypothesis statement that is in fact true. And it makes sense why that's a bad thing, because you never want to reject truth. You always want to embrace truth, accept truth, okay? But the nice thing about hypothesis testing is we have an idea as to what level of risk we run should we decide to reject the null hypothesis and opt for the alternative hypothesis as being a truthful statement. We also, in step 2, compute our critical values, and the critical values depend upon your level of significance. And basically, ladies and gentlemen, your level of significance is going to determine the size of your rejection region or regions in the standard normal distribution. If you're conducting a one-tailed test, specifically like an upper tail test, then your rejection region will be in the upper tail of the standard normal distribution. And the size of that rejection region will be alpha, your level of significance. If you're conducting a lower tail test, then your rejection region will be found in the lower tail of the standard normal distribution. And its size again would be alpha, your level of significance that you set. If you're conducting a two-tailed test, then you're going to have two rejection regions of equal size, one in the lower tail and one in the upper tail of the standard normal distribution. And the size of these rejection regions is going to be your level of significance alpha divided by 2. Alpha divided by 2. Okay. The region that is not the rejection region is called the do not reject region. It's the region within which, if our test statistic falls in the region or in that interval, we would not reject our null hypothesis. Okay. All right, step number 3, we're going to compute the test statistic by using our formula that we've seen on the other page. Our z-test statistic is going to be the sample mean minus the purported unknown population mean under the null statement, divided by the standard error of the sampling distribution. That's your test statistic. In step number 4, we then determine in what interval our test statistic falls by comparing it to our critical z value. This is your critical z value here. For a two-tailed test, your critical z values are equal in value but opposite in signs. If our test statistic, okay, is more extreme than our critical z value or values, then we will reject the null hypothesis. If our test statistic is less extreme than our critical value or values, then we will fail to reject the null hypothesis. We will not reject the null hypothesis. And the last step, by far, really is the most important step of this entire procedure, because it summarizes in plain English the results of our test. And I think I indicated last week that when you state your conclusion, please do state it in a plain, simple English statement that maybe a 10 or 11-year-old could even understand. Do not use technical jargon like my test indicated that my test statistic was more extreme than my critical z value, therefore I will reject the null hypothesis. Somebody that doesn't understand anything about hypothesis testing would not understand a word you just said. So make sure that you water it down, okay, so that, like I said, a layperson can understand what you're saying here. You could say something to the effect that I conducted a hypothesis test, and you know what? The conclusion is that the population mean appears to be greater than like 50. Okay. Or the mean number of defects during an operational day in churning out maybe ball bearings on a machine is indicates that the mean diameter exceeds 50 millimeters. And they can understand and appreciate what you just said there. But if you just say, you know, like I said, my z-test indicates that I can reject the null hypothesis, we're not really going to be able to appreciate what the test is really indicating. Okay, so your conclusion is very important to state it in a way that, like I said, lay people can understand and appreciate what you're saying. All right, so there are 5 steps here. All right, here's an example. A researcher believes that the average number of hours a person spends in traffic each year is more than the national average of 46 hours. Notice the word believes is a hunch, ladies and gentlemen. It's a gut feeling. And therefore, that's a thesis, okay, or a hypothesis that needs to be basically researched for its truth value. And the way to do that is to conduct formal hypothesis testing to test this belief and see if it is indeed true. Assume that the population standard deviation is 3.6 hours. Now, I have a question for you. When they're saying that the average number of hours a person spends in traffic each year is more than the national average of 46 hours, what's their definition of traffic? What does that mean? I mean, when we get in our car or truck, we drive down the road, there's always somebody around us. So what do you think that means, ladies and gentlemen? To spend time in traffic. We all spend time in traffic when we get on the road. Can anybody, I don't know, lend some insight into that? How do you interpret that? What does it mean to be spending time in traffic?
Heavy traffic, like not moving as much.
Heavy traffic, maybe like a traffic jam or something? You know, yeah, like maybe it's almost a complete slowdown. Do you agree? That's how I'm interpreting this. Because we're all subject to traffic on the road. It's got to be, you know, the number of times that you're caught in maybe like a traffic tie-up or something. I mean, that's the only thing I can think of. Because that's a very general thing to say, traffic. So I guess that's what they're saying, or that's how I'm interpreting it. Like you're caught in some sort of a tie-up for maybe like 30 minutes. Okay, they jot that down for the year. You were caught in a traffic tie-up for 30 minutes on a given day. And they keep track of all the time throughout the year that you had, you know, experienced such a thing, right? Anyways, this researcher believes that the average number of hours spent in traffic, maybe a traffic tie-up during the year, exceeds the national average of 46 hours. Assume the population standard deviation is 3.6 hours. Suppose that we randomly sample 30 subjects and we find that the mean time of these 30 subjects that they spent in traffic tie-ups is 47.8 hours. Test a claim at 5%. Now, ladies and gentlemen, why do we even have to bother with hypothesis testing here? We can clearly see that this sample mean wait time in traffic tie-ups is 47.8 hours. That obviously exceeds 46 hours, the national average. What's the flaw in using this one sample in trying to draw an inference or a conjecture about the unknown population mean amount of time that everybody spends in traffic tie-ups? Can anybody maybe shed some light on what the flaw is in using just one sample here? What's the problem with that? Yeah, it looks like the hunch or the claim is being satisfied by this one sample mean, but what's the problem with that? There's a big flaw in that. I'll give you a hint. Is one sample enough? Is one sample mean good enough to make a conjecture about an unknown population mean? Yes or no?
No.
No. I mean, I could reach into this population and sample 30 other subjects, and maybe their mean wait time in traffic tie-ups is like 42 hours. Oh, well, that's less than the national average. And maybe I pull another sample of size 30 out, and I find that their sample mean wait time is like 46 hours. And maybe I sample another, sample size 30, and I find that their mean wait time is 50 hours. Well, I have a question here. How many samples of size 30 can you extract from a large population? There might be hundreds of thousands of samples of size 30 that you can extract from this parent population, and each one would have a different mean. So which sample mean is the accurate mean as to guesstimating what the unknown population mean is? You see the problem there? Some sample means would be less than 46 hours. Some sample means would be greater than 46 hours. So which one do you use? There's the problem. So ladies and gentlemen, you can't just use one sample mean, okay, to try to infer what an unknown population mean is, especially for a sample that's much smaller than the size of your population, because you have no measure as to how accurate or how far off that sample mean is in approximating the actual unknown population mean. Therefore, you must, okay, do a formal hypothesis test or build a formal confidence interval where you have the central limit theorem go to bat with you and the concept of this sampling distribution of all sample means of a certain size extracted from the parent population. So you have to use probability theory here, right? That's the only way in order to conduct formal hypothesis testing or to build a formal confidence interval and to do justice to this problem. All right, so step number one, we have to first of all indicate what hypotheses we're testing. Well, ladies and gentlemen, notice that the researcher believes that the average number of hours a person spends in traffic tie-ups in a year is more than 46 hours. More than suggests what inequality symbol? More than. Greater than, do you agree? So therefore, that would have to be our alternative hypothesis statement. Everybody see that there? Because remember, I said the alternative statement's always greater than, or less than, or not equal to. Therefore, for this particular problem, it appears that our alternative hypothesis is the claim that we are testing. It is the claim that we are hoping sample evidence in formal hypothesis testing tells us is the truthful statement. It's our hope that our claim is supported by sample evidence and hypothesis testing. But we'll find out. By the way, the null hypothesis would be saying that the population mean wait time is equal to 46 hours and not greater than 46 hours. All right, so that's step number one, where you establish clearly your hypotheses that you're testing. Step number two is you need to determine at what level you're going to test at. Notice they want us to test at what, 5%. And I have a question for you, ladies and gentlemen. Is this going to be an upper or lower tail test? The answer lies in the symbol used for the alternative hypothesis statement. Is this an upper tail test, lower tail test, or two-tail test? Anybody? Look at your alternative hypothesis inequality. What does it say? Greater than? So that means this is going to be what kind of a test?
Upper.
An upper tail test, where the rejection region is going to be found in the upper tail of the standard normal probability distribution here. And we have to find this critical value, okay, that separates the upper tail rejection region from the other interval below the critical Z value, which is the do not reject the null hypothesis interval or region. And notice the size of this rejection has to be equal to the level of significance that we're testing at, which is 5%. So 0.05 is the upper tail area of the rejection region. So that leaves 95% of the area of the entire curve, which represents the do not reject null hypothesis region or area. And so then we got to find this critical value. How are we going to find this critical value? We would use our what function on our calculator? Would we use our normal CDF or inverse norm function? What do you think? Normal CDF or inverse norm?
Inverse norm?
Yep, the inverse norm finds critical Z values. The normal CDF finds probabilities or areas. We already know the area is 5%. We want to find this critical Z value here. So in order to do that, we would go grab our inverse norm function on our calculator, and we would have to type in the area that's to the left of our critical Z value that we seek, and the area would be 0.95, comma, the standard deviation of the standard normal distribution is 0, I'm sorry, the mean of the standard normal distribution is 0, and the mean is, the standard deviation is, the mean of the standard normal distribution is 0, and the standard deviation of the standard normal distribution is 1. That's what you'd have to type in. Go ahead and do that. And can anybody tell me what this critical Z value will be that separates the rejection from the do not reject region? What's that critical Z value?
1.64.
All right, so positive 1.64 is the separation value that separates the upper tail rejection of the null hypothesis region versus the lower part of the curve, or the lower region, which is the do not reject null hypothesis region. All right. Okay, so step number 2 has been completed. We set our level of significance alpha. We use that to find our critical Z value in conducting this one tail or upper tail test. And we've clearly established the rejection versus the what? Do not reject region. And again, keep in mind, this is the do not reject region. Do not reject the null hypothesis region. The upper tail is the rejection of the null hypothesis region. All right, step number 3 is to compute the test statistic, and that's based on sample evidence. So we reached into our parent population and pulled out a sample of size 30, and we computed its mean to be 47.8 hours, minus the purported mean of the population under the null statement, which says the population mean is equal to 46. Divided by the standard error of the sampling distribution of all sample means, okay, of all samples of size 30 that were extracted from the parent population. And that could number in the hundreds of thousands or even millions of samples that you could extract. All right, so we divide this by the known standard deviation of the population, 3.6 hours, divided by the square root of the sample size, which is 30. You get on your calculator and dial that up. By the way, make sure you enclose your numerator inside parentheses if you crank this out on your calculator. You should get about 2.74 as being our test statistic value. All right, so that's our test statistic. So we've conducted steps 1, 2, and 3. Step 1, again, was establishing the hypotheses that need to be tested. Step 2 was setting a level of significance alpha and determining our critical Z value and establishing our rejection, do not reject rejection region. Step number 3 was computing the test statistic value. There's only 2 more steps that remain. Step 4 is determining what we're going to do. What's our decision? Is a sample evidence strong enough to suggest that we're able to reject the null hypothesis or not? And then step number 5 is, once we make our decision, what would be our conclusion in plain English so that a 12-year-old can understand what we just did? Okay. All right. So we have 2 more steps to conduct. Any questions about these first 3 steps here? All right. So let's move on here. All right, ladies and gentlemen, now step number 4 is making a decision. And here's how we're going to make that decision. Using the standard normal probability distribution and the fact that our critical Z value is 1.65 right there, which separates our upper tail rejection region from the rest of the interval down here, which is the do not reject region. What was our test statistic value we computed back in step 3 on the previous slide? Wasn't it 2.74? Notice 2.74, ladies and gentlemen, our test statistic value, which is 2.74, is greater than our critical Z value, which is 1.65. Because of that, our test statistic falls in the upper tail rejection region of the standard normal distribution. And because our test statistic falls in the rejection region, we are going to reject the null hypothesis. We are going to reject the null hypothesis. And therefore, we're going to state in plain English our conclusion or our summary. And our summary and conclusion is that sample evidence is strong enough to suggest that the mean wait time of all people that drive, and there could be millions and millions of people that drive, exceeds 46 hours, which is the national average. And we only stand a 1% chance of having rejected a null hypothesis that may be true. What percent chance, ladies and gentlemen, do we have of committing a type 1 error? Of rejecting a null hypothesis and spouting off and saying that then the average time that all drivers spend in traffic tie-ups is greater than 46 hours. We stand a 1% chance of making a big mistake in saying that.
5%.
5, because that was our level of significance that we, the researchers, set. That's the level of risk that we, will have to fathom in making this bold conjecture and saying that the mean number of hours that everybody spends in traffic tie-ups is greater than 46 hours. We only stand a 5% chance of committing a type 1 error. Okay, a type 1 error. All right. Now, I have a question for you. Is that a lot of risk? Well, the only one that can determine if this is a risk worth taking and making a bold conjecture about a population parameter is the researcher, him or herself. That's the only one that can make that determination. Does that seem like a lot of risk, 5%? Yeah, I mean, it doesn't seem like it. I mean, only a 5% chance of making a big mistake and saying that the average time everybody spends in traffic tie-ups exceeds 46 hours. Doesn't seem like it. So I have a question. Why not test at 1%? Why doink around, ladies and gentlemen, at 5% when we can lower the risk all the way down to 1%? Why don't we do that? Well, I'm going to show you that there's a little dilemma, a little paradox. The same dilemma that we experience when building confidence intervals, where we've seen that if you increase your level of confidence, your confidence interval gets wider. And so you decrease the amount of precision in trying to, pinpoint exactly what value the unknown population mean is, because you got a lot of values to choose from in a wide interval. If you lower your level of confidence, you're less confident that your population mean is even in your confidence interval, but your precision increases in the sense that you have less values to actually, pinpoint as being your population mean if it's even in your confidence interval. So there's a trade-off between confidence and precision. Same thing with hypothesis testing. We have a trade-off going on here. For instance, if I lowered my level of significance from 5% down to 1%, question, ladies and gentlemen, what's that going to do to the size of my rejection region? Is it going to make the rejection region larger in size or smaller? If I reduce alpha, my level of significance from 5% down to 1%. What do you think it's going to do to the size of my rejection region? Make it larger or smaller? Remember, alpha is the size of your rejection region. So is my rejection region going to be larger or smaller if I reduce the level of significance from 5% down to 1%?
Smaller.
It's going to be smaller. Do you agree? What's going to happen is this critical Z value is going to move further to the right and get closer and closer to our test statistic value. In fact, ladies and gentlemen, if I reduce my level of significance from 5% down to 1%, you know what's possible? What's possible is my critical Z value could move to the right of my test statistic value. Now I would have a much smaller rejection region. But what happened? What happened is my test statistic now is no longer found in the rejection region. It's found in the do not reject region. It's found in the do not reject the null hypothesis region. So here's the problem. Yeah, ladies and gentlemen, we could lower our level of risk from 5% down to 1%. And then if we reject the null hypothesis, we only stand a 1% chance of committing a type 1 error as opposed to a 5% chance. But the problem is if you lower your level of significance, you decrease the size of your rejection region, you move your critical Z value further and further to the right, which may in fact force our test statistic to no longer even fall in the rejection region. In which case you would not be able to even reject your null hypothesis at 1%. So there's a little problem, a little trade-off here, okay? As opposed to if you increase your level of significance from 5% up to 10%, if you increase it from 5% up to 10%, that's going to cause your critical z-value to move further and further to the left and further away from your test statistic, forcing it even more conclusively inside your rejection region. Yeah, it becomes even more stronger evidence to suggest that if we test at a larger level of significance, we'll definitely be able to reject that large level of significance. But the problem is, ladies and gentlemen, you're also increasing your chance of committing a what? Type 1 error in rejecting the null hypothesis. So you see the little problem we got going on here. You lower your level of risk, but your rejection region decreases in size, forcing your test statistic to actually, in most cases, fall outside of the rejection region, in which case you can't even reject anymore the null hypothesis, not at that level of significance. But if you increase your level of significance, and in all honesty, you could increase your level of significance to any value where you could always reject your null hypothesis. But keep in mind, when you increase your level of significance, you're also increasing the chance of committing a type 1 error, of rejecting a null hypothesis that in fact may be true. And that's a bad thing to commit a type 1 error. Okay. So there's an inevitable trade-off. I got a question for you, ladies and gentlemen. How can we have our cake and ice cream and eat them both? What was the moral of the story when constructing confidence intervals? To maintain a high level of confidence and a high level of precision. Increase the size of your what?
Your sample.
Your sample. That's right. That's the only way out of this little dilemma, this trade-off in hypothesis testing. Okay. To maintain, okay, a rejection region that would have our test statistic lie in, and also have a very low level of risk of committing a type 1 error, we would have to increase the size of our sample. That's the only way to get those two good things together, right? But again, are we in a position to increase our sample size? Maybe we don't have the resources or the time. So it's just like this juggling act that we have to kind of deal with these inevitable trade-offs, these little dilemmas with building confidence intervals and now doing hypothesis testing. All right. Normally, 10% is considered to be a pretty large risk. In 10% or more for a level of significance is too much risk to even think of rejecting your null hypothesis. You could, but you stand a large chance of committing a type 1 error. So normally, you only want to reject your null hypothesis, usually at no more than about 5%, or certainly as low as 1%, you can reject your null hypothesis. Okay, the 10% is getting up there. Okay. So, all right, now here is another example. 1 year, the average score on the SAT math test was 515. Scores on the SAT are normally distributed with a population standard deviation of 100. A local high school randomly selects 36 students to see if the students are doing worse than the average on the SAT math test. In other words, on average, is this high school scoring less than 515 on this SAT test? 515 is the average score, the national average score, I am assuming here. All right, now here's the scores of those 36 randomly selected high school students. These are the scores that they attained on that SAT test. And notice they're all over the place here. The question is there enough evidence to support the claim that the students did worse than the national average if we test at 10%? First of all, step number one, what would be our hypotheses we're testing? Notice the claim is that the students on average scored lower than the national average. Lower than means what inequality symbol? Lower than 515. means less than. Do you agree? Well, that's going to be our null hypothesis. That's our claim that we're testing. That's our alternative hypothesis. That's our claim. Our null hypothesis says that the the mean score for all students in this high school on the SAT math test would be equal to 515. So this is going to be a lower or left tailed test, since our alternative hypothesis statement has the less than symbol. And the size of that lower rejection region in the lower tail of the standard normal distribution is going to be 10% of the entire area of the standard normal curve. So we have to find a critical Z value that separates the lower tail rejection region from the upper tail acceptance region, and that would be negative 1.28, which could be found using your inverse norm function on your calculator. Okay. And now we have to reach into our parent population, and we have to pull out what? A sample, good sample. And we did right here. 36 is our sample. We need to find the sample mean. So to find the sample mean score of these 36 randomly surveyed high school students, we would have to maybe put these into a list in our calculator and use the 1-bar stats function, correct? To find X bar. I think they've already done that on the slide here, so we're not going to take the time to do that right now. They did find the sample mean to be 509.028 for those 36 scores. Now we're going to compute our test statistic value, which is step number 3 of the 5-step procedure in hypothesis testing. You take the sample mean and subtract off the purported population mean under the null statement. Under the null hypothesis statement, the unknown population purported mean is 515. So we take our sample mean, subtract off 515, and divide it by the standard error of the sampling distribution of sample means, which is to say the population standard deviation, which is 100. They gave that to us. Divided by the square root of the sample size, which is the square root of 36. When you crank that out, you'll have your test statistic, which is negative 0.36. Now comes step number 4. Ladies and gentlemen, where does my test statistic fall in relation to my critical Z value, which is negative 1.28? Well, notice that my test statistic, negative 0.36, is greater than my critical Z value, negative 1.28. So it falls safely in the what? Do not reject null hypothesis interval or region. And therefore, we fail to reject the null hypothesis, or we cannot, or we do not reject the null hypothesis for this test. And so, ladies and gentlemen, I have a question for you. Does sample evidence, is it strong enough to suggest that the mean score of all these high school students will be less than the national average of 515? In other words, can we go with the claim as being the truthful statement if we fail to reject the null hypothesis? Yes or no?
Yes.
Well, let's go back. These are our hypotheses. The claim was the alternative statement that says the mean score of all these high school students on the SAT math exam will be less than the national average of 515. That was the claim. But look at, we just conducted hypothesis testing and we're unable to reject the null hypothesis. We cannot reject the null hypothesis. So the claim is not being supported here by sample evidence and by the central limit theorem, all right, and by probability theory. So the claim is not being supported here, ladies and gentlemen, because we failed to reject the null hypothesis here. And again, we fail to reject the null hypothesis because our test statistic, which is negative 0.36, does not fall in this lower tail rejection region, because negative 0.36 is not less than negative 1.28, our critical Z value, but it's greater than negative 1.28. It's just making sense why we fail to reject the null here. We could not reject the null hypothesis here. Now, what level did I test at? I tested at 10%. Do you agree? 10%? I believe this, yeah, it was the level of significance we tested at. I have a question later on. What if I increase my level of significance to be about 49%? Could I reject then? If I drove alpha's value all the way up to about 49%, what would happen to the size of my rejection region? Well, it would grow it would grow to a very large size. Do you agree? It would become huge. This would be my rejection region now, correct? And notice my critical Z value now would be what? Greater than my test statistic, forcing my test statistic negative 0.36 to fall in the rejection region. Sure, we can reject at 49%, but what's the problem in doing that? Why would we not want to reject the null hypothesis at 49% level of significance and say, yes, our high school students are going to score less than 515, less than the national average? Why would you not want to make that bold statement or bold conjecture, ladies and gentlemen? What's the danger in that? Sure, we can reject at 49%. We can reject at 98%. We can reject at 68%. What's the problem with that? Why don't we just increase the level of significance up to a point whereby the test statistic is forced into the rejection region? What's the problem in that? We could reject the null hypothesis at 49%, but we stand a what percent chance of committing a type 1 error now? We stand a what percent chance of committing a major blunderous type 1 error? We stand a 49% chance. Do you agree? That is way too much risk. Okay. So there's no way you want to reject the null hypothesis here, not for this test. The test statistic falls way too safely into the do not reject the null hypothesis region. It's too far away from your critical Z value down here. There's no way you want to drive alpha all the way up to 49% or higher, and then, with confidence, reject the null hypothesis and go with the claim. So it doesn't look like sample evidence is supporting the claim at all here, right? Too much risk in rejecting a null hypothesis there. All right, here's another one. A random sample of 40 adults skipped breakfast on an average of 51.2 times per year. Assume the population standard deviation is 3.1. Can we conclude at a 1% significant level that the population mean for the number of breakfasts skipped per year is not 50? Not 50 times? Well, to say not 50 means to say it is or it is not equal to 50, which means our hypotheses are pretty much cemented by that statement. So therefore, our alternative hypothesis would be saying that the mean number of breakfasts skipped by all adults is not equal to 50. That would be the claim. And the null hypothesis says that, yes, the mean number of breakfasts skipped by all adults in the population is equal to 50. Okay. So, ladies and gentlemen, what kind of a test is this going to be? One tail or two tail?
Two tail.
Two tail, because we got the not equal to symbol in our alternative statement. That means we're going to have two rejection regions, one in the lower tail and one in the upper tail of the standard normal probability distribution, the size of which is going to be our level of significance, which is 1% divided by what? 2. So the size of this lower tail rejection region is going to be alpha divided by 2, which means it's going to be 1% divided by 2. And what's 1% divided by 2? Well, that's a very small area. Do you agree? That's going to be 0.005. 005. 0.005. That's the size of your lower and upper tail rejection region. Getting on your calculator, dialing up the inverse norm function, you would find that the critical Z value would be negative 2.58, and the upper tail critical Z value would be positive 2.58. Now we compute our test statistic. Notice the sample mean from 40 randomly sampled adults was 51.2 minus the purported population mean of the population under by the purported population mean under the null hypothesis, which was equal to 50, divided by the standard error of the sampling distribution, which is to say the standard deviation of the population, which is known to be 3.1, divided by the square root of the sample size, which is square root of 40. Your test statistic is 2.45. where does 2.45 fall in relation to these critical Z values? Does it fall in between negative 2.58 and positive 2.58? Or is it more extreme than the upper or the lower critical Z values? Where does it fall? Does it fall in the rejection region, or does it fall in the do not reject region? What's the conclusion here?
In the do not reject region.
Exactly. It's a little less, not much less, but it is less than the upper tail critical Z value of 2.58. So it does fall in the do not reject region. And so therefore, yeah, I mean, it doesn't look like at 1% that we're able to reject the null hypothesis. Okay, we cannot reject the null hypothesis at 1%. And therefore, it doesn't look like at 1% level of significance that our claim is being supported here. Because we cannot reject the null hypothesis and conclude the alternative is a truthful statement. So the claim is not being supported here. So we fail to reject the null hypothesis. And all we can say is that sample evidence is not strong enough to support the claim that the mean number of breakfasts missed during the year is different than 50. We cannot go with that. We cannot say that because we cannot reject the null hypothesis. Now I have a question for you. If I increase my level of significance from 1% to 5%, do you think we might be able to reject the null hypothesis then? If I drove alpha's value up to 5%.
Yes.
Yeah, I think we probably would be able to reject the null hypothesis if we increased alpha up to 5%, because that's going to cause these critical Z values to move closer to the mean of the distribution. So these critical Z values are going to move closer to the mean of the distribution, increasing the size of your rejection region, which will then force the test statistic of 2.45 into the upper tail rejection region. So ladies and gentlemen, we might not be able to reject at 1%, but we might be able to reject the null hypothesis and go with the claim as being a truthful statement at 5%. Granted, we do stand a little larger risk of committing a type 1 error in doing that, from 1% up to 5% risk now. But, you know, if that still doesn't seem like a lot of risk for you, the researcher, if you're willing to take 5% risk, then go ahead. You can then reject your null hypothesis and say, okay, no, it looks like the claim is being supported by sample evidence. You do stand a 5% chance of making a big mistake in saying that. But, you know, I mean, is that a risk you're willing to take? Are you in a position financially to take a risk like that? Maybe. If you are, most researchers would probably say, yeah, I'll just increase alpha a little bit to force my test statistic in the rejection region, and then I'll reject my null hypothesis. All right. So yeah, this test here is not extremely conclusive, because just by increasing your level of significance a little bit from 1%, by increasing a little bit from 1%, it looks like we're able to reject the null hypothesis. Okay, so this is not an extremely conclusive test like the last one. The last one was you'd have to drive up alpha all the way up to at least about 49% before you could finally reject the null. You would never, under any circumstances in that case, we don't want to reject the null hypothesis. Way too much risk in that situation. But here, it looks like you could still get away with rejecting the null and not really have that much risk. Maybe what, 4 or 5% risk of committing a type 1 error. All right. Now, ladies and gentlemen, there is a way to conduct these tests using our calculator, and the function that we would use would be called the z-test function. So this is a function that basically circumvents us having to go through steps number 2 and 3. So we could basically just run the z-test and make our decision very quickly. But in doing that, we have to make use of a probability called a p-value to make a decision. A p-value is a conditional probability. And the p-value is saying that given that the null hypothesis statement is true, what's the probability of obtaining, okay, a test statistic as extreme or more extreme than the one we actually obtained from our parent population. And I believe there was a saying that had a rhyme to it last week. Does anybody remember that little rhyming statement with regards to the p-value? It says, hold on a second. It says for p small, we do what? Reject
The
the
null.
null. Do you agree? For p small, reject the null. And the way it works is this. If you have a very small p-value, then that's rather overwhelming evidence to suggest that your null hypothesis is probably not true at all. Okay? If you have a very large p-value, then that lends more credence to the fact that your null hypothesis may in fact be true, and we should not be rejecting the null hypothesis. And if you want to be even more sure about whether or not, given a p-value, to reject or not reject the null hypothesis and what level of risk you stand, the way it works is this. If your p-value is less than your level of significance alpha, then you would want to reject the null hypothesis. Okay? Then you want to reject the null. If your p-value is larger than your level of significance, then you cannot reject the null, or you fail to reject the null hypothesis. Cannot reject the null hypothesis. So that's the way it works, ladies and gentlemen, with the p-value. Okay? So your calculator is not going to, give you critical z values. It's not going to tell you whether your test statistic falls in the rejection or the do not reject region. It's just going to compute what's called a p-value, and you, the researcher, has to use that p-value to make a decision as to whether or not you're going to reject the null hypothesis. Okay? So your calculator computes a p-value, and the p-value, like I said, is a conditional probability based on the sample test statistic that you actually computed from the sample you extracted from your population. All right, so for p small, reject the null. Okay. So I'm gonna, you know what I'm gonna do? I'm gonna back up here. I'm gonna do some of these problems over again, but this time we're gonna use our calculator, okay? Let's do this problem over again, but this time let's use our calculator. Hold on a second here. Why is this not showing? Okay, but I can't, hold on. What in the heck is the deal here? How come this is not being rendered the way it normally renders itself? Deal here. View. Normal view. Well, let me ask you this. Can you guys see my calculator up here or not?
Yep.
You can see it. Okay. All right, let's do this traffic problem over again. Remember, we worked it out manually, and we came out with our test statistic of 2.74, and we were able to reject the null hypothesis, and therefore state that the claim that the mean wait time for all drivers exceeds the national average of 46 hours was being supported. Okay. So let's do this problem over again, but this time let's use our calculator and use the z-test to conduct this hypothesis test instead of the formal 5-step manual way of doing it. All right, so what we're gonna do is we're gonna hit our stat button, go over to tests, and it's number 1. It's the z-test. So we want to dive into the z-test. We're going to use stats that are already computed from our sample. What is the purported mean of the population under the null hypothesis? It's 46. The standard deviation of our population was given to us to be 3.6 in this problem. The sample mean was 47.8 hours, and the sample size was 30. Notice this is to conduct a two-tailed test, this is to conduct a lower tail test, and this is to conduct an upper tail test. Notice because of our alternative hypothesis and equality symbol, we are doing an upper tail test. You must select this one, upper tail. Then just go down to calculate, ladies and gentlemen, and hit enter, and boom. Notice your test statistic is computed to be about 2.7386, blah, 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 which is the 2.74 that was manually computed using the formula. And notice we get a p-value, which is 0.003. What level did we test at for this problem? Wasn't it the 5% level? So I have a question for you. Is my p-value, which is 0.003, greater than or less than 5%?
Less than?
A lot less than, do you agree? 0.003 is less than 0.05, which is my level of significance. And therefore, ladies and gentlemen, for p small, we're going to do what? For p small, we
Reject.
reject the null. And that's exactly what happened when doing the problem manually. We were able to reject the null hypothesis. You see how this is working here? In fact, ladies and gentlemen, we could even lower alpha down to 1% and still reject the null hypothesis. Do you agree? Isn't 0.003 even less than 0.01? Wouldn't this be even less than 1% level of significance? We could still reject the null hypothesis even at a low level of significance of 1%. For that reason, this is called an extremely conclusive test. No question whatsoever that you would want to reject your null hypothesis, and you would stand a very, very, very small chance of committing a type 1 error. That's why we call this a conclusive test. Okay? Does that make sense there? So you definitely want to reject the null hypothesis here, and you could drive alpha all the way down to, gosh, even 0.005. Do you agree? You could even reject at 1/2 of 1%. And you'd only stand 1/2 of 1% chance of committing a type 1 error if you reject your null hypothesis. So this is an extremely conclusive test. No doubt whatsoever to reject the null hypothesis here. All right, so that one's done. Let's go on. Let's do this next one here. All right. Here we're testing to see whether this high school's mean score on this SAT math test is less than national average. At 1%, wait, excuse me, at what level of significance? At 10%, we were unable to reject the null hypothesis at 10%. Okay, let's conduct this test now using our calculator. All right, so stat, test, z-test. Stats are already computed. Under the null hypothesis, the mean of the population is 515. Standard deviation for this test is what? What was the standard deviation? 100. What was the sample mean? What was the sample mean? 509.028. Sample size was 36. Okay. This is what kind of a test? It's a lower tail test. Must select lower tail, go down to calculate. And we're ready to conduct a z-test, and it's done. Notice our test statistic is about negative 0.358, negative 0.36 is what they got using the formula. Notice our p-value is 0.36. Ladies and gentlemen, is that a large or small p-value, 0.36? Well, I'll tell you one thing, that p-value of 0.36 is certainly larger than 1% level of significance. It's larger than 5% level of significance. Heck, it's even larger than 10% level of significance. So what do you think? Would we reject the null hypothesis here for this test? Is that a small p-value or a large p-value?
Large, not reject.
This is large. That's way too much risk to be rejecting a null hypothesis here. That's a very large p-value. In fact, to be able to reject your null hypothesis, you would have to drive alpha's value up to at least about 37% or higher. So if you drove alpha's value up to about 37%, oh, you could reject the null hypothesis then. The problem is you go right ahead and do so, but you stand a 37% chance of committing a type 1 error. And that's a bad thing. It's the worst thing that could happen in hypothesis testing. That's way too much risk, ladies. I'm going to be rejecting a null hypothesis here. And that is also made evident with the fact that this test statistic value is so far away from this critical Z value. Because our test statistic falls so safely in the do not reject region, this is overwhelming evidence to suggest that no way would you ever want to reject the null hypothesis here. Way too much risk. And that's being indicated also by our very large p-value. All right, so this is a very conclusive test to not reject the null hypothesis. Is this making any sense how we're conducting hypothesis testing using the z-test on our calculator and using the p-value to make a decision? Just remember, for p small, you can reject the null. For p large, don't do it. Way too much risk. All right. Here's another example here. A researcher claims that the average wind speed in a certain city is 8 miles per hour. The claim is that the wind speed is equal to 8 miles per hour. So what would be my alternative statement? What symbol would it be? If I said that the claim is that the mean wind speed mu is equal to 8 miles per hour, you would say the alternative statement would be that mu is what?
Not 8 miles per hour.
Not
equal to 8 miles per hour. Exactly. That's your alternative hypothesis statement. So in this case, notice the claim is not the alternative statement. The claim in this case is the null hypothesis statement. So don't think the claim always has to be the alternative statement. Sometimes it's the null statement. It just depends what your claim is and what you're testing. Okay. Those are the hypotheses that we would test formally here. To do so, we're going to need sample evidence. And they chose 32 days at random and discovered that the average wind speed over those 32 days was 8.2 miles per hour. Standard deviation of the population wind speed is 0.6 miles per hour. And they want you to test at 5%. Is there enough evidence to suggest that our claim is true? Well, let's use our calculator to conduct this test. And so therefore, we will bring our machine up and conduct a z-test. So we're not going to do it manually by showing all 5 steps here. We're just going to go to stat, tests, z-test, and we already have sample stats computed. The sample mean wind speed, the population mean wind speed under the null hypothesis statement or the claim is that it's 8 miles per hour. Population standard deviation wind speed is 0.6 miles per hour. The sample mean wind speed is 8.2 miles per hour. The sample size was 32 days. And this is what kind of a test? It's a two-tailed test. Do you agree? Because the alternative statement is not equal to. Go down and calculate. It's that simple. We're ready to do our z-test. And the test is done. The test statistic from sample evidence is 1.89. The p-value is 0.059. Got a question for you, ladies and gentlemen. Is my p-value larger than or less than my level of significance of 5%? I was testing at 5%. Notice my p-value is a little bit greater than my level of significance of 5%. Do you agree? Not by much, but it is. And therefore, can I reject the null hypothesis at 5% here? Can I reject the null hypothesis at 5% here?
No.
Oh, the answer is no, because my p-value is a little larger than my level of significance of 5%. Listen to this question. Could I increase my level of significance from 5% up to 6% and be able to reject my null hypothesis? What if I increase my level of risk of committing to type 1 error by 1% from 5% up to 6% chance? Could I reject my null hypothesis now?
Yes.
Yes, I could, because now my p-value is what? Less than, do you agree? My level of significance. But I do stand a little larger risk in rejecting that null hypothesis. But do you think that's a significant amount of risk increase in going from 5% to 6%, Leno? I don't know. I mean, that doesn't seem like a huge amount of risk increase. Do you agree? Going up by 1%. So you know what? My question is this. Is this a very, 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 without a doubt or without a question, a conclusive test to not reject the null hypothesis? Yes or no? Is this a very conclusive, overwhelming situation to say that we will never reject our null hypothesis? Is that the case here?
No.
Not at all. In fact, if you just increase your level of significance up by 1% higher than 5% to just pithy 6%, you could finally reject your null hypothesis. And that's not really a huge amount of risk going from 5% to 6%. Okay. So it really doesn't look like the claim is being supported here in an overwhelming sense by sample evidence. Ladies and gentlemen, it would be if your p-value was very, very large. Do you agree? Like if your p-value was like 59%, 0.59, yes. In that case, you would say your claim is being overwhelmingly supported by sample evidence and the central limit there. But that's not the case here. Just by budging your level of significance from 5% up to 6%, you can finally reject your null hypothesis. So the bottom line is, it really doesn't look like the claim is being, supported overwhelmingly by sample evidence here. It's not being supported. Granted, if you lower, if you increase your level of significance or lower your level of significance all the way down to 1%, you cannot reject. You cannot reject at 4%. You can't even reject at 5%, but you can reject at 6%. And I don't really think personally that 6% is a tremendous amount of, risk in committing to type 1 error. Remember I said, once you get above about 10% or higher, then you're starting to incur way too much risk. And it's too much of a gamble then to be rejecting your null hypothesis. Usually statisticians agree that once you get up to about a 10% risk or higher for your level of significance in rejecting your null, you don't want to reject your null hypothesis under those circumstances. But 6%, that's still within reason. So in this case, yeah, because we can't reject at 5%, but we can reject at 6%, I would say in an overall sense, I don't think this claim is being supported at all. I don't think it's being supported. No. So, all right. Sometimes your tests do split hairs, okay? Most of the time, they're very conclusive one way or another. All right. Okay, so here's some guidelines that statisticians in a universal way agree when conducting hypothesis tests. And if your p-value is less than or equal to 1%, reject the null hypothesis. The difference is highly significant. Meaning, ladies and gentlemen, you definitely want to reject the null hypothesis and don't worry about committing a type 1 error. Very conclusive test right here. If your p-value is greater than 1%, but less than or equal to 5%, you still want to reject your null hypothesis, and the difference is significant, okay? So you don't even have to worry about, committing a type 1 error here. If your p-value is greater than 5%, but less than or equal to 10%, consider the consequence of committing a type 1 error before rejecting the null hypothesis. But ladies, remember, I only went from 5% up to 6% in the last test. That's only a measly 1% higher than 5%. So I would still be inclined to lean towards saying, I think we can reject the null hypothesis, okay? So it's still probably okay to reject a null hypothesis, and you still stand a relatively small chance of committing a type 1 error. But if your p-value is greater than 0.10, do not reject the null hypothesis. Now the difference is not significant between your test statistic and your actual your purported hypothesized value of your population parameter, in which case, ladies and gentlemen, you do not want to reject the null hypothesis. To do so would have you taking way too much risk in committing a type 1 error. So again, if your level of risk is 10% or higher, usually we do not never want to reject the null hypothesis. Okay, so those are like a rule of thumbs as to when you would lean one way or another in deciding to reject or do not reject your null hypothesis there. Okay. All right, well, let's go on into our textbook and see what kind of trouble we get into. Let's see here. All right, let's go to section 8.2 and see if we can have some fun. So this is going to be section 8.2. And section 8.2 is entitled Z-test for a mean, okay? All right, as always, you can look down through the examples and stuff, but we're going to cut through the chase here. Okay, now, problem number 1 here, ladies and gentlemen. The average depth of the Hudson Bay, which is up in Canada, is 305 feet. I didn't know that until I read that today. That's interesting. So Hudson Bay on average is about 305 feet deep, give or take. Climatologists were interested in seeing if the warming and ice melt were affecting the water level. 55 measurements over a period of randomly selected weeks yielded a sample mean of 306.2 feet. The population variance is known to be 3.6 feet. Variance is squared, though. That'd be square feet. So what are you going to have to do to bring the population variance down to units that are similar to the mean? Take the what of 3.6? Remember, that's a variance.
The square root.
You got to take the square root to find the standard deviation. So don't forget to do that. Your population standard deviation is the square root of 3.6. It's not 3.6. This is the variance. That would be the standard deviation. Can it be concluded at the 5% level of significance that the average depth has increased? All right, ladies and gentlemen, step number 1. What would be the hypotheses we'd be testing here? Can it be concluded at the 5% level of significance that the average depth has increased? Wait a minute, increased from what? Increased from what? What value? Increased from what value? Well, what was the purported average? What is the believed average depth of Hudson Bay?
305.
That's right. So therefore, these would be the hypotheses that you'd want to test. Everybody see in there? And what would be your claim here? Would it be the alternative or the null hypothesis statement? Let's go back and read it one more time there. What would be the claim? Can it be concluded that at the 5% level of significance that the average depth has increased? Is there evidence? Is there evidence of what caused this to happen? Well, so the claim kind of lies with what statement, the null or the alternative, based on what it is they want to test. What do you think? Where's the claim? Seems like it would reside with what? Not the null, but the what? Seems like it would reside with the alternative hypothesis statement. And we're testing at what, 5%? Okay. All right, so ladies and gentlemen, here's what I want you to do. I've done step number what? 1 and a part of step number 2 in assigning alpha to 0.05. I want you to finish steps 2. Okay. Step 2, defining your rejection acceptance region, finding the critical values and all that stuff. Step 3, computing the test statistic. Step 4, and then step 5, a plain English conclusion as to what our test is indicating. We'll call this classwork number 1. I want you to do the rest of step 2, 3, 4, and 5. I've done step 1 in setting up the hypotheses for you. I did a part of step 2 in indicating what alpha is. You need to finish step 2 and do step 3, 4, and 5. Okay? See if you can do that. We'll call this classwork number 1. And you want me to go back to the problem in the textbook? Do we have this written down here? Okay. All right. There you go. All right, go ahead and finish steps 2, 3, and 4. 2, 3, 4, and 5. Classwork 1. All right, so these are the hypotheses we're testing. Testing at 5%, it's an upper tail test. The rejection regions found in the upper tail of the standard normal distribution. Using the inverse norm function, type in the area to the left of that critical Z value of 0.95, 0.1. We get 1.64. Your critical Z value is 1.64. The test statistic is now computed by taking the sample mean, 306.2, minusing the purported population mean under the null, which is 305 feet, divided by the standard error of the sampling distribution, which is the population standard deviation, which is a square root of 3.6. Remember, they gave you the variance in this problem. You got to find the standard deviation by taking the square root of the variance, the square root of 3.6, which is about 1.9, divided by the square root of the sample size of 55. Test statistic about 4.68. Notice my test statistic 4.68 is greater, rather much greater than my critical Z value, so it falls very safely in the upper tail rejection region. So this looks like a rather conclusive test to suggest that we will reject the null hypothesis. And therefore, ladies and gentlemen, in plain English, we would say that sample evidence supports the claim that the water level is indeed rising. Did anybody do that test and get those results there?
Yep.
All right. So that's doing the test manually, correct? So I have a question for you. If we do this test using our Z test on our calculator, would we expect the p-value to be large or small? Would we expect a large or small p-value? If this is a conclusive test, which it looks like it is.
Small.
Yeah, we would expect us to get a very small p-value, right? I want you guys to go ahead and do that now. I want you to conduct this test using your Z-test function on your calculator. Convince yourself you get a very small p-value, smaller than 0.05. Go ahead, try that out. So now I want you to do this test over again using your calculator, your Z-test function. All right, let's check it out here. Z-test, go in there, enter, select stats. Reported mean of the population under the null is 305 feet. Standard deviation of the population is known to be 1.90, about. Sample mean depth was for 55 randomly sampled areas of the lake was 306.2 feet. And there were 55 randomly selected areas of lake that were surveyed as far as its depth is concerned. This is an upper tail test. And I'll just calculate. And there you go. You get a p-value, which is, notice your test statistic is 4.68. That's what we got using the formula. Got a question for you. Is this a large or small p-value? Well, if you read it as 1.4, that's an error because this is a probability. Probabilities cannot be larger than 1. No, you got to look further to the right. It says e to the -6. What does that mean? What does this e -6 mean? Is this a large or small p-value here?
Very small.
Very, very small. That's scientific notation. So this is an extremely conclusive test, ladies and gentlemen. No doubt whatsoever of rejecting your null hypothesis here. You definitely want to reject. You don't have to worry about committing any type of one-year error. All right. This p-value in decimal notation is going to be like 0.1234514088378. Do you agree that's a very small p-value? That is so much smaller than even 1% level significance. You could drive alpha all the way down to something dirt and almost non-existent and still be able to reject the null hypothesis. So there's no way you have to even worry about committing a type 1 error with a p-value this small. You definitely want to reject. And that was made very evident also by the fact that my test statistic is far away, tucked very, very safely into the rejection region. It's not even close to flirting with the critical Z value. It's way up here. That indicates that this is a very conclusive test. And that's why we should not be surprised to see such a small p-value. Okay. Is this making any sense, ladies? I'm in the manual way versus the p-value method. This way of doing the problem, showing all 5 steps, is called the critical value method. Critical value method. The method we use in our calculator is called the p-value method. P-value. Both methods concur with the same conclusion and the same result. All right. Okay, that was classwork number 1. Okay, well, let's see here. All right, try number 5 here. Now we're getting pressed for time. Whoops. We're getting pressed for time, ladies. So I want you to do number 5. I want you still to set up your hypotheses. Make sure you write down your hypotheses that you're testing. And then I want you just to conduct the test using your z-test function in the calculator and come up with a conclusion. So let's do number 5, classwork number 2. Still write the hypotheses down so we know what we're testing. And then take it from there using the calculator. Oh. So these would be the hypotheses that you're testing for number 5 here. It's a lower tail test. And this is the claim. Those are the hypotheses. All right, now do the test on your calculator. So that's how you would have to populate your z-test fields. And let's go down and calculate it. All right. Is that a small or large p-value? Notice your test statistic is negative 2.2627417. You would find it out by using your formula if you wanted to. Is that a p-value, a very small or large p-value? That's a small p-value. We would be able to reject at 5%. We could reject the null hypothesis at 4%. We could reject the null hypothesis at 3%. We could reject the null hypothesis at 2%. We could not reject at 1%. It's close. But ladies and gentlemen, I think this is pretty conclusive that we're definitely going to reject the null hypothesis. Can anybody in plain English to explain to us what is this test? What is this test just shown us? Pretend you're trying to explain this to a 12-year-old kid. How would you state the conclusion? You don't say I reject the null hypothesis. They're not even gonna know what you're talking about. What did we show? What is this test showing?
That there's less caffeine in tea bags now.
How much less? Less than
26.
26 milligrams. Yeah. Yeah. I mean, a layperson can understand what you just said there. Hey, in these new tea bags they just came out with, there's less than 26 milligrams of caffeine. Well, they might not understand what a milligram is, but at least they can understand what you just said in general. All right. So yeah, always try to, paint the conclusion in terms that a layperson can understand, because if you're doing, rendering your findings at like a board meeting, like for a company, a lot of the people may not even know anything about statistics. Okay, so that's very important. All right, ladies and gentlemen, number 7. This is the last one here. You're going to have to put this data into you're going to have to put your data into a list and then find the mean of this sample here. So go ahead. We'll call this the last classwork today. Notice it says at the 5% level, can it be concluded the average height differs from 29 inches? Therefore, this would be a two-tailed test. You go ahead and conduct this test using your z-test function on your calculator. I'll write the hypotheses out right here. So what I did is I entered the data into my list here. And the hypotheses we'd be testing would be the null says the mean height is equal to 29 inches versus the alternative that says the mean, the unknown population mean height is not equal to 29 inches. And the standard deviation is 2.61. You know, we might not even have to find the mean of the sample. We should be able to just conduct the test by using data instead of stats. So get out of this, go to stat, test, z-test, and just select data. Reported mean is 29. No, it is 26, excuse me. Standard deviation of the population is known to be what? 2.61. List 1, frequency 1, and this is a two-tailed test. And just go down to calculate, you know, it should be that simple. I think your calculator is automatically going to compute the mean of your data in list 1. It'll automatically, don't worry about that. Just calculate. And there you go. Your test statistic would be 7.24. Notice this p-value is, oh geez, this p-value is essentially non-existent. It's extremely, extremely small. Therefore, you definitely can reject the null hypothesis at any level of significance. Don't even have to worry at all about committing a type 1 error. And so, ladies and gentlemen, it does look like the population mean height is different than 29 inches. So it looks like the claim is being overwhelmingly, supported by sample evidence. All right. That p-value is extremely small. No doubt, reject the null hypothesis. Anybody come up with that?
Yep.
All right. So today we looked at testing for an unknown population mean where the population deviation is known. For that reason, we use the Z distribution. That's why we call this a Z-test. In 2 days, we will assume we do not know the population standard deviation, in which case we'll have to use as a point estimate the sample standard deviation. In such a case, however, we have to use a different continuous distribution called a T distribution to conduct the hypothesis test for the unknown population mean. That's called a T-test. We'll look at that in 2 days. All right, ladies and gentlemen, I'll stay on the line. If there's any questions that you might have or concerns, you might want to let me know. If not, have a good day.